So apart from bringing you back to break, I've got the pleasure to introduce Christine King, Director of the Gateway for Accelerated Innovation in Nuclear. Christine's primary focus at GAIN is to facilitate public-private partnerships to move innovative nuclear energy technologies forward towards commercialization. Christine brings insight from 27 years of private sector experience, a bachelor's in chemical engineering from North Carolina State University, and an MBA from Lynchburg College. Welcome, Christine.
Hey, y'all. You say that here, right? So I'm kind of last on the agenda. And since we're at school, I feel like we need to do a little bit of a review. So you're gonna see some things that you've probably seen before today, but I'm gonna point out a few different things about it. And what I'm hoping is that today you have ignited your nuclear curiosity. And at the end of my presentation, I'm gonna give you some places where you can go get some additional information. But before we get there, just a little bit more about me. So I've been in nuclear for 32 years. So clearly I like this technology. I'm not here to make you like this technology. That's your decision. Actually, the role of the national labs is to bring you unbiased information about all technologies. Now, I come into the national labs 5 years ago with an expertise of commercializing technology. So my expertise is helping us get things from benchtop out to commercial scale. And what do those business models look like? And the joy that I have is our team is very, very service-oriented in helping people find the information or the facilities or the scientists that they need. The Office of Nuclear Energy wants to make sure that what we have learned over decades of doing not only nuclear research, but operating nuclear reactors, that's used and useful as we pursue these new reactors. So let's get into it a little bit. Okay, so we saw this before and we heard some discussions about it. So what I want to point out is I want you, all of us, as we pursue new energy systems in this country, we need to remember that we are operating an energy system that was gifted to us from the generation before. And what we have the opportunity to do is to gift the next generation a robust energy system as well. So what I've learned in this job is you actually have to come at this as an energy professional. And you have to focus on the end first. You have to think about what you want to use this for before you decide on the kind of reactor or any kind of generating technology you might want. It's kind of like buying a car. So I'm going to go with Ford, since I heard earlier your governor is a Ford dealer. So we're going to go buy a new car, and you go to a Ford dealership. Do you ask them to sell you the best car? If you do, there's probably 15 questions that salesman's going to ask you. How many people do you need to be in it? Are you going to take it off-road? Are you going to tow with it? Do you just want it to be comfortable? And are you looking for a hybrid option or a full electric, right? It's the same thing in picking a reactor technology. There's many, many questions you need to answer about it relative to how you're going to use it. And then as you think about that, you can start to think about the size of that technology. You can think about what you need it to do, whether you need it to produce just electricity alone, or do you want to dual purpose it? And doing that dual purposing, as we think about process heat, that can be an excellent way for us to partner with our industrial organizations, our industrial factories and manufacturers. In some cases, though, some of the manufacturers out there need higher heat loads than we can provide. And it may be that the correct answer for them is to continue to get their heat from natural gas. So don't be surprised by that answer. Okay, and also, here's the other thing I want you to remember. Small modular reactor, that's marketing language. So if you ever have a developer in front of you that's selling a small modular reactor, you should ask them, what does that mean to you? Because for some of them, they're small-ish, right? They're like 300 to 400 megawatts. That's still pretty big. And in some cases, modularity is about having multiple modules that are small, or the modularity is about building the modules in a factory setting and deploying them for assembly on site. Okay, so how are we going to use it? And if somebody's selling you an SMR, you ask them what that means to them. Microreactors. This is something that I just think is fascinating. This is looking at small, transportable, factory-fabricated reactors. Some of them are meant to operate for 20 years once you turn them on. Some of them are designed to have a fail-safe of always on. So there are significant places, or there's specific places in the United States and globally where this makes a lot of sense. So if you think about replacing diesel generators in some mining operations, these could be very good options. You think about islanded countries or islanded states. This could be a good option for them to always have electricity no matter the weather event that comes their way. So yes, they are transportable in the back of an 18-wheeler, and there is discussion on what part of the regulations actually need to apply to a microreactor because the design is so different. And there are proposals in front of the NRC to look at how we can quickly approve these designs and get them to market. At my lab, at Idaho National Lab, if you want to look into this a little bit more, look up Project Pele, P-E-L-E. That is a project that we're doing in conjunction with DoD. All right, the next marketing language you're gonna hear, active, passive, and inherent safety. Okay, so today's plants we have an active safety scheme. Okay, that means you need some sort of interaction, external input for that safety system to operate. I want you to think about that like an airbag. So when someone hits your car, it causes the airbag to deploy. If you have a loss of coolant accident, you need an electrical input to open that valve to get your makeup water. Okay, so those are the types, when we talk about active safety in our existing fleet, that's what we mean. Now, in our new reactors, you hear a lot about passive safety and inherent safety. So let's talk about passive first. Passive, again, is this is taking advantage of some engineering choices that you can make. Okay, so what happens to hot air? That's where you answer. It rises, and cold air comes down. We're taking advantage of that in the internal, that's just about the internal stored energy in those two fluids, right? Or in that fluid. Air is a fluid. So when we build our reactors and we make them subgrade, this is how you can trigger that natural circulation. What does that allow for? That allows for us to have continual cooling of the reactor without having to have external power. The way to think about that is if you've ever been on scaffolding, I would guess that probably people doing props here in the theater have been on scaffolding. Hopefully they're on a self-retracting line. Self-retracting lifelines, they allow you to move around and do the work that you need. But if you were to fall, as soon as that line has that significant increase, it triggers the brake and it stops your fall. So passive and natural circulation is a similar kind of philosophy. Inherent safety. So this is really taking advantage of the physics of some of these reactors. So for fast reactors, we have what's called a negative power reactivity coefficient. What that means is as the reactor gets hotter, the nuclear reaction itself is less efficient and it shuts itself down. Think about that. The way I like to think about that is the quick disconnect shutoff valve that's at the fuel pump. So now everybody's going to go gas up tonight and you're going to look at this. This protects the gas station. If you, for some reason, forgot to take the nozzle out of your vehicle and you drove off, you're going to beat the living snot out of your car with that valve on the end. But the gas station would be protected and it would prevent, that valve would close and it would prevent gas from being sprayed all over the gas station. So these are the types of safety features that are being designed into the new reactors. So when you get to be in front of a developer, the second question you should ask them is, how have you designed passive or inherent safety into your system? And how does that show up? And how does that change the way you deploy the reactor or operate it in the future? Okay, so one of the things I'd like to think about, so we have, Doug True told us this morning, we have 94 operating reactors. We're looking at restarting Palisades, Palisades and the Crane Energy Island in Pennsylvania. So we'll have 96 reactors. That's about 100 gigawatts of power. Right now, we are working to extend the license of those plants out to 2070 by operating them through 80 years. So what does that mean? Second license renewal is kind of like those milestone birthdays with your doctor, right? You turn 40 or 50, and there's a whole new series of screening tests that you have to go because our body degrades, our body ages, everything does. So our plants age as well. So these standardized tests that we do at the end of a 40-year license life or a 60-year license life are very similar to those milestone appointments with your doctor, where you're going to do some standard screening tests, and what you do going forward depends on the history of how you've operated that nuclear power plant, the results of those tests, and that sets your maintenance policy going forward. So that's how we are able to extend the license of those power plants to 80 years. By extending the license of our existing fleet to 80 years, we're going to operate today's fleet into 2070. And that gives us, I think, the coping time that we need as we look at the energy demand. Now, before AI came along, we had increasing energy demand. AI is just exacerbating the situation right now and causing a significant increase in demand in a very short period of time. Looking at this particular picture, what I want you to take away, so on the, hang on, let me get it, on the left-hand side, on the left-hand side, you see the two large hyperbolic cooling towers. That's what our plants look like today. There's 1,000 megawatt plants. And if you look at the Vogtle plant, that's before Vogtle 3 and 4 were built, you can see the footprint of that plant is 600 acres, and the emergency planning zone is 10 miles. As an example here, we're showing the schematic of an X-Energy plant. X-Energy they have 4 modules called XE100s. So engineers are really creative. That's 100 megawatts per module. So a 400 megawatt facility. I'm sorry, this says 80 megawatts electric. But their plant footprint is much smaller. It's 10 acres. And the emergency planning zone is expected to be less than a mile or at site boundary. And the reason for that is because they don't have as much fissile material in the reactor. So our emergency planning zones are based on the worst case scenario of entraining fissile material into a plume, and then that's your evacuation zone. So we had the emergency folks here early talking about the types of drills they run for Callaway, should that happen. The other difference we have in some of these reactors, whoops, I'm gonna come back to that, is that by not operating with water, some of them are actually operating at much lower pressures. So when we go to build these, we don't have to build those thick-walled pipes anymore. We can use thinner pipes, and it gives us the opportunity to also work with that a little bit better in a factory setting. Spent nuclear fuel, otherwise known as waste. So just the lifespan of and this is for our pressurized water reactors or our boiling water reactors that we operate today. So we saw the fuel pellet. I know, let's see, we've heard Pinky today. I like to say gummy bear, but it's a very small ceramic pellet. And the fuel we're planning to use in some of the advanced reactors is a ceramic as well. It's not as small. The TRISO fuel is not as small as a gummy bear. And the other difference is in some cases, it's about the size of a golf ball. Some folks are designing that fuel form to be about the size of a billiard ball. So there's some differences that are coming out there. The other difference is it has more enriched uranium than our existing fleet. So these fuel pellets have 3 to 5% concentration of uranium in fissile uranium in them. For our advanced reactors, we're looking at using up to 19% enriched uranium. That allows us to have a more efficient nuclear reaction, and it also allows us to use more of that fissile material before we pull it out of the reactor. A fuel assembly will spend about 6 years in a reactor today. After that, it spends about 5 years in a spent fuel pool thermally cooling off. And once it thermally cools off, we load things into a dry cask system. And you saw pictures of that earlier today. And we've heard parking lot, concrete pad. This is not the original way we planned to store our fuel, but it is safe. The original plan was that fuel utilities would depend on the Department of Energy to pick that fuel up and store it long term. And the Department of Energy is still working on that. This is what it looks like. So for DC Cook in Michigan, this is all of the fuel that they used for 49 years of operation. These casks are dual purpose casks. So they are good for storage, and they're also good for transportation. So we don't need to do anything else to them to take them to a permanent disposal facility. Now, with new reactors, we open up the potential for recycling some of the fissile material that's left. I mentioned just a moment ago that we don't use all of the fissile material in our existing fleet. And we don't. There's a significant amount of fissile material left, and it's called closing the fuel cycle when you recycle. Other countries have closed their fuel cycle successfully, and one of the reasons to do that is not only to gather the fissile material and reuse it, it also reduces the volume of waste you have to manage on the back end. Licensing. So the Nuclear Regulatory Commission, so this is your third question, if you're ever in front of an advanced reactor company. How's it going with the Nuclear Regulatory Commission? If you are licensing a commercial reactor, most of them participate in what's called pre-application engagement. That's kind of like taking a draft of your thesis to your professor before, like your draft or a rough outline, before you really start to get into the details and write that out. And you start to surface some of the questions that they might have. And that makes for a better application. We've seen this where the NRC, because of these pre-application engagements, when an application shows up, they're able to accept that application faster than they have in the past. The other thing you want to ask them is, where have you filed for your license? And there's a couple of different licenses they can file for. What you're going to see right now is a two-step process. A lot of folks are going in to get their construction license. That allows them to start civil construction and a little bit of nuclear construction on their site. It does not allow for construction of the plant itself. You would come back later after you have a certified design of the reactor to get a build permit and a build license. That's just for the next five or so years. Once we have certified designs, you would just go in for what's called a COLA, which is a combined construction and operating license. This is what I want you to think about in terms of an advanced reactor and designing it and licensing it and operating it. It's just like somebody, we're going to go back to Ford again, designing a new car. So Ford can design a new car. The NTSB is responsible for telling them, here's the ways that we want you to test that to prove that that car is safe. You, as the operator, are responsible for getting a license, typically a state license, to demonstrate that you can operate that machine safely. We're operating a bigger machine, but it's not radically different. The process is essentially the same. What's going on at the states? A lot. So for the past, I would say, in the late, like 2015 to 2020 or so, a lot of the discussion about advanced nuclear was inside the Beltway in DC. And there was a lot of federal discussion. What we have seen in the past few years is the states getting incredibly involved. Here, we're just talking about the different working groups and feasibility studies that have been taken on at a state level. 18 of these feasibility studies have been completed. We have them on the GAIN website. We have links to them if you would like to read these feasibility studies. Some of them, sorry, that's really small. So some of them are just about reviewing the technology itself. Some of them look at specifically in Kentucky and Maryland, they were looking at fossil fuel transition. Some of them look at community engagement and education, and what do we need to have a workforce for this? And I mention this because this would be a great jumping off place for Missouri to look at some of these studies that have already been done and determine what gaps you may have and pursue those. There's a lot of work that has been done in this space. Okay. So if you're like me, it takes a long time to make a decision. So I'm not ready to pick my reactor, but I know one day I'm going to want one. What can I do? So there is a process with the NRC called an early site permit. It allows you to pick a bounding technology, let's say an SMR at 600 megawatts, water cooled. That's what I want to build. you are able to take that operating envelope and go ahead and do the environmental work and the community engagement work to site your plant there one day. So you take that plant parameter envelope, you apply for an early site permit that says, I know this piece of property passes the environmental and nuclear siting regulations, and you get a permit for 20 years. When you're ready to pick your technology, you go back to the NRC, you say, I'm gonna build this technology, it fits in my previous analysis, and you get a license for construction. So this is one way, as these technologies are still under innovation, if you're not quite ready to pick one yet, you can pursue an early site permit. It allows you to get started in the community that's interested in building the technology and hosting it in the future. So Doug talked about this earlier today. His map and my map are a little bit different. This is a map from Third Way and Nuclear Innovation Alliance. The numbers are, his is a little more up to date than mine, and this is from last summer. But what I want you to take away from this is, if you looked at this map for Europe, you would not see microreactors. You would see primarily small modular reactors or large reactors as being the types of things that they want to deploy in the future. And that's just because of the energy needs that they have. They have a significant number of coal stations that are retiring, and they're trying to replace that energy. Here you see, remember back when I started, we talked about how do you want to use it in the end. Here you see microreactors being in that role for different end uses in the United States and North America. We have 32 active projects in North America. We have 12 deployment dates before 2030. I'm not here to tell you that we're going to have 12 new reactors by 2030. You should chase me out of the auditorium if I did. But what I can tell you is, from where those agreements were 2 years ago, we have progressed. There is a variety of agreements, everything from a memorandum of understanding, but 7 of these have firm contracts. So we are moving towards deployment, and we are getting, the investments and the buyers to build these plants. Okay, now that you're nuclear curious, somewhat nuclear informed, I wanted to give you a few different places where you can stay up to date. The U.S. Department of Energy, Office of Nuclear Energy, they have a great YouTube channel. And I've been working with the Office of Nuclear Energy, and I also work with some of the others here. We have been working hard to get our engineers to put their decimal points in their pocket and talk in plain language about nuclear energy. So these are resources that are written in plain English without acronym if you're interested in exploring the technology further. If you still can't find the answer you want and you have a question, our team is very, very service-oriented. You can reach us through email, you can reach us through our website. My phone number is plastered all over all sorts of different places. Our goal is to help anyone that's part of the conversation and part of the decision associated with a nuclear technology, is to have the information that you need to participate in that decision. So please don't be shy. I have folks that go, well, you're really busy. I don't care. Call me anyway. And we'll do the best that we can to find the information that you need. Thank you.
Thank you, Christine. I'm Matt Sanford. I'm the Executive Director of the MU Research Reactor. This has been a great day for nuclear and for Missouri and for Mizzou. I just have a couple of comments before I hand it over to Kurt Schaefer for final remarks. I can certainly say I think this event has surprised me, and I think it's evidence of the real resurgence of need and interest in nuclear here in Missouri. And tying back to President Choi's remarks this morning, at the same time as this topic today, there is a boom also happening in nuclear medicine, and that is fueled by incredibly exciting advances in the fight against cancer using radioisotopes to save and extend lives. And those are not possible, just like nuclear energy, without nuclear reactors. And that is the reason, primarily, for the NextGen MUR initiative here at the University of Missouri. And I'll just also mention that while we're operating the Mizzou reactor at MUR, we are training a nuclear workforce, and we're doing that along with our friends at Missouri S&T, training reactor operators, health physics technicians, nuclear manufacturing technicians, shipping. We have a ballooning internship program, and many of them are here today learning. And we're teaching all of them, our students and everyone in every discipline, about nuclear safety culture. I'd also like to say it was a pleasure meeting so many of the experts in this room. Incredible expertise here today. And we appreciate the support we've received from many of you and the offers of support to help us make our initiative a reality as we work to build what will be the first new research reactor in the United States in over 40 years. We have many reasons to be excited about nuclear here in Missouri. And with that, I'd like to reintroduce Kurt Schaefer.
Well, in closing out, I want to thank everybody for coming. I think we heard a lot of great information today, and I think when you listen to the fact that we're anticipating 3% annual growth potentially the next 15 years till 2040, and the requirements that's going to put on people in the industry to make sure that we've got cost-effective, reliable power in the state of Missouri and beyond, you really start to look at all the alternatives, especially with the matchup of some of the things that are going on in concern with climate and looking at dispatchable power that does not have a carbon footprint. It really leads to bringing nuclear back into the discussion. So I want to thank all of our speakers today and our panels who really gave us a lot to think about. I think we're advancing this discussion forward. I want to thank the University of Missouri for providing us this wonderful venue here at the beautiful Missouri Theater to have this event. I want to thank the National Governors Association. You haven't seen it, but they've got staff behind the scenes who helped put this together and been running this all day, and they've done a fantastic job. The U.S. Department of Energy, who was critical in making sure that we had this opportunity to put this on. And I really want to thank Emily Wilbur and the Division of Energy at the Department of Natural Resources who put all this together. They did a fantastic job. So please, hopefully this gave you a lot to think about. Go home and we'll advance this discussion more as we move forward. So let's give a hand to everybody who spoke today. Thank you very much.